problems, I just wanted to give you a review of the equations that are involved. And we talked about all these equations the other day. And this makes up the entire chapter 25, which is current electricity. You know that it is the flow of electrons. And current is defined as Q by T, the rate of flow of charge. Q is the charge in coulombs, time in seconds, and then you will get current in amperes. And actually it is nothing but coulomb per second. So 1 ampere is 1 coulomb of charge flowing in 1 second. And the symbol for ampere is not AMP, it's just an A, capital A. That's the symbol for ampere. And this is Ohm's law, very important. Current is the ratio of the potential difference or voltage to the resistance. So I stands for intensity of current, because we always use C for the speed of light. That's the voltage applied, and R is the resistance of the cable or the conductor. Voltage is in volts, resistance is in ohms, and of course current is in ampere. And the symbol for ohm is the omega. Therefore we can also define an ampere as 1 volt divided by 1 ohm. So that's another definition for ampere from Ohm's law. Resistance depends on 4 factors, and here we have 3 of those factors. The resistance of a conductor depends on the material, which is represented by the resistivity of that material, the length of the conductor, and the area of cross-section. Resistance is in ohms, length is in meters, and area must be in meters squared. Rho is the resistivity, its unit is ohm meter. We know that resistivity for conductors is of the order of 10 to the negative 8 ohm meter. For semiconductors it is 10 to the negative 3 to negative 5. And for insulators, it could be 10 to the positive 13 to 10 to the 15. So resistivity is a constant for each material. Then we look at the 4th factor that affects resistance, and that's temperature. And this is how the relation is, where RT is the resistance at T degrees Celsius. R0 is the resistance at 0 degrees Celsius or 20 degrees Celsius, because that's the room temperature around that. And alpha is a constant again for each material. It has a different value. It's called the temperature coefficient of resistance. The temperature coefficient of resistance. All right. So finally, you know that alpha would be in, the unit of alpha would be per degree Celsius, per degree Celsius. That would be the unit of alpha. So you just find a number per degree Celsius showing how much its resistance changes for every degree change in temperature. Power is the product of voltage and current, electrical power. P is measured in volts, I is measured in amperes, therefore power must be in volt ampere. But that's the same as the unit for power, usually watts, right? It's the same thing. So 1 watt is 1 volt ampere. But there are 2 other formulas that you could use, and you know how we get those just by using Ohm's law. If you substitute for I as V divided by R, you're going to get V squared by R, right? So just substitution from Ohm's law. Now this here is very crucial because there are 3 formulas and you cannot use all 3 of them. You can only use one of them. It depends on the situation. And how do we find that situation? Which one? You have to look at what is the constant. We're going to have a practice of that. What is a constant? And pick that equation that has the constant as one term. For example, if the resistance is constant, you're not going to use this because that one does not have resistance. If the current is constant in the problem, then you cannot use this because there's no current there. So we'll have more practice about that. But basically, those are the equations for electrical power. And then taking a microscopic view of current, we know that the current through a conductor depends on the number of electrons in 1 meter cube, the area of cross-section, the drift velocity of the electrons, and the charge of the electrons. So those are those terms. And okay, I'll stop it right there. Let me just remind me, is current a vector or is it a scalar? Okay, it's a scalar quantity. N is, again, remember, number of electrons in 1 meter cube. It is not the total number of electrons. It is the number of electrons in 1 meter cube. Usually students forget that. So A is the area of cross-section, and usually cables are circular in cross-section, so that will be pi r squared, right? And this is the drift velocity, which is normally small. Drift velocity is really tiny. It's like 10 to the negative 5 meter per second. E is the charge of the electron, which is 1.6 times 10 to the negative 19 coulombs. Now from that one, we can define what is called the current density. J is called the current density. Now current density is a vector. That's a big difference. Although current is a scalar, current density is a vector. And current density is defined as the ratio of the current to the area. So it's simply I by A. I by A. Therefore, the unit of current density would be ampere per meter squared. And it's a vector, again, it's a vector. It has a direction. But we can also show that it's defined at, okay, surely when you divide this by A, the A cancels out, so you know that current density is NVE, right? Because the A will cancel out from there. So that's one way to calculate the current density. Another way to calculate current density is to use this formula, sigma E. And do you know what E is? E is the electric field. And how do we calculate the electric field if we are talking about a cable? If you're talking about a conductor like this with a potential difference between the two ends, how do you find the electric field? If you know the voltage between the two ends. And of course you know the length of the conductor. Correct. Electric field is just the ratio of the voltage to the length. Because E is V over D, remember. So that, and sigma is called the current density. Oh, and it's related to the resistivity. Look at that, resistivity here. Did I say current density? I'm sorry, J is the current density. Sigma is called conductivity. This is resistivity, right? 1 by resistivity is called conductivity. So it's the reciprocal of resistivity. That's what it is. So you have 3 ways of calculating current density. Simply the ratio of I by A or I to A. Second, NVE. Third, sigma E, where sigma is 1 by rho. All right. Now there are 2 types of currents, AC and DC. I don't know whether we talked about this. We did not talk so much about this. What does an electric cell produce? We call it a battery, but that's wrong. You cannot call it a battery. No. What is this actually? What does this represent? It's an electric cell. Electric cell. Now you only call it a battery when you have more than one connected, technically. But you know, we usually call everything a battery anyway. So that's a battery. But you can also say this is a DC source. a source of direct current. Why? Because if you connect a resistance to this, we know that the current is always going to flow in one direction, isn't it? Current always flows from positive to negative. The magnitude of the current is the same, the direction is the same. For example, if this is 5 volt and this is 5 ohm, what's the current? So you begin talking, that's why I'm asking you. 5 volt and 5 ohm, what's the current?
1 amp.
Thanks. 1 ampere. Is that current going to change? No, it's constant in magnitude. Is the direction going to change? No. That's why it's called a direct current. But the current that these lines carry, they could be represented this way. Where on the x-axis you have time, on the y-axis you have the magnitude of the current. Isn't it clear that the current is changing? It's a sine curve. So the current goes from 0, as you can see, the current goes from 0 there to a peak value, back to a 0. And what is this? How do you explain that? I mean, in waves we call it a trough, but in electric current, what does that mean? It simply means it's flowing in the opposite direction. So all this time it's flowing in one direction, and here it's flowing in the opposite direction. Again it switches. That's why it's called an alternating current. It alternates directions. And how many times does that change? On these lines it changes 60 times in a second. So we say that the frequency of AC here is 60 hertz. That's it. It switches 60 times in a second. Do we feel it? No, we don't. Why don't we feel it? Chiefly because we're using it for lighting purposes, and the direction of current doesn't matter there. It doesn't matter. But if you're using electronics, it does matter. And remember that whenever we use electronics, although we are supplying AC to it, actually we are converting it into DC before it gets it. So for a computer or whatever electronics it is, it's actually DC that's powering it, although we give it AC. So there must be something that converts AC into DC, and that is called a rectifier. To rectify means to correct. Now what does it correct? It corrects these undulations. It corrects the variations and makes it like constant. We'll come to that later on. At the end of electricity, we'll look at all that stuff. But just know that this is AC. This is the little part that I did not teach, so I'm going to finish this and then we'll do problems. But there is a real problem here. What is the average value of AC? If you take the average of that, what will you get? 0. So if I draw another AC that has a bigger peak value, let's say that much, what will be the average value of that? 0. So now, does that mean that these two are the same? No. We definitely know that this is more powerful. So if you take the average value, you're going to come to the wrong conclusion that they are the same. So we cannot take the average value to compare AC. So what do we need to do? To compare AC, this is what we're going to do. We'll take that AC source and connect it to a resistance. Take that AC source, connect it to a resistance, and heat will be produced, isn't it? Whether it flows in one direction or the other direction, heat will always be produced. So let's say that the heat produced by this AC source in 1 second is 5 joules. Then what we'll do is, we'll take that AC source, remove it, and connect a DC source, which produces the same heat in the same time. You heard me? And let's say that this is 2 volt. Now, since the AC source produces the same heat that is produced by 2 volt DC, we're going to say that the DC value of that AC source is 2 volts. Does that make any sense? The DC value of that AC source is 2 volt. So we define it using heat produced, because heat produced doesn't depend on the direction. So, but there are 3 names for that. That's a problem now. It's called the DC value. It's called the root mean squared value. or it's called the effective value. All these three mean the same. And you can actually calculate it using the peak value. I'm going to show you now. You can calculate this from the peak value. I hope I've written it. If that's the peak value and it's represented by I naught, then the RMS value is I naught by root 2. That's how you calculate it. If you know the peak value, just divide it by the square root of 2, you will get the RMS value. Again, remember, it's the RMS value, the DC value, or the effective value. Same thing. In the same way, the RMS value of voltage can also be related by a similar relation. Remember, this is a chapter on its own. AC is a chapter on its own, and that's the last chapter. We're coming to that later on. This is just a fundamental idea to compare AC with DC. Okay, so that's not the end of AC. And that's the most interesting chapter. It's coming. Right now, that's enough.
I have a question. What were you using for I naught and V naught?
I naught is the peak value of current, and V naught is the peak value of, yeah. Then we talked about electricity charges. I think we did, didn't we? How the electric company bills us. Yeah, I just wanted to go over that. Kilowatt hour is 1 unit. For example, if a 100-watt lamp is used for 10 hours, then we know it's 100 watts times 10 hours. That gives us in watt hours, isn't it? And then divided by 1,000, you will get it in kilowatt hour. We went through this, so this is just a review before you start doing the problems. So I think that's it. So question 1. Resistance is 9.6 ohms. You're asked to find the current. Voltage is 240 volt. Of course, it's Ohm's law that you're using. I is equal to V over R. Just divide and you get 25 ampere. And then to find the charge that passes, use I is Q over T. Time has got to be in seconds. So 50 minutes is 50 times 60 seconds. It's 75,000 coulombs. When you read the second question, you've got to look at those numbers. This light bulb has a resistance of 12 ohms at 20 degrees Celsius and 140 ohms when it's hot. Look at the value of alpha. What do you think? Is it small or big? It's really small. So that means, that is how much the resistance changes for 1 degree Celsius. And if the resistance should go from 12 to 140, you know that the temperature is going to be really, very high. It's going to be really hot. So you have to, read the question and get an idea before you start plugging it into the equations, please. In this case, the formula is RT is R naught 1 plus alpha T minus T naught. We'll save time because I know everybody can substitute. So I made RT by R naught minus 1. It's on the left side now. And then now I can get T minus T naught if I divide that whole thing by alpha. And therefore to get T, divide the whole thing plus T naught. Now I substitute at the end. You may probably be carrying the numbers through all the steps, I do not know. And I get 1797.8 degrees Celsius. Goodness, that is really hot. Temperature of a filament. That's why these light bulbs are called incandescent lamps. You know that. That means they produce light by heating. Did we talk about? Yeah, I think I mentioned that only 5% is converted into light, 95% converted into heat. And here is the reason. It's so hot. But why don't we feel the heat outside? I mean, If you go and touch the light bulb, it's going to be hot, but it's not going to appear to be that hot. Anybody knows the reason why?
Because there's no gas inside, is it? Or
Oh, so it's either evacuated, right? So the only process by which heat can come out is by radiation. You've cut out conduction and convection. Or sometimes, or most of the time, it's an inert gas filling it. Why should we have an inert gas inside the light bulb?
high capacity for heat?
High capacity? This is another reason, because what happens if you heat a metal in oxygen? I gave it out. It'll catch fire. It'll get oxidized. And when it gets oxidized, the metal loses all its properties and becomes so brittle. Right? We don't want that to happen. So we do not want it to get oxidized, so we have it filled with an inert gas. Make sure that the metal doesn't react with that. No oxidation chances. That's why. Okay? Calculate the ratio of the resistance of a 10 meter of aluminum wire, 2 meters in diameter, to 20 meters of copper, 2.5 millimeters in diameter. The resistivities of both are given. You know that the formula to be used is resistance is rho L by A, right? And then set it up as 2. That's the resistance of aluminum divided by the resistance of copper. I know Cu is the symbol for copper. Okay, so when you write that, isn't that what you get? Obviously, I have switched sides for this because you know when you divide, you invert it and multiply. That's what I've done. And then just substitute the numbers, not a big thing. And area is, of course, pi r squared. What's given is not the radius, right? So you got to take half of that, change it into meters. So I've done all that. Millimeters is changed into meters. That's why there is 10 to the negative 3. That's pi r squared because it's the area. I just put these two one below the other. I collected them, you know what I mean. Those are the ratio of the lengths, and it's so boring when you don't have to think. You just 1 by 2 and then find that ratio and get it as 2.65 times 10 to the minus 8, and then those are the resistivities. Final answer 1.232. What's the unit of the final answer? David, I got you. Or rather, I got you. It's a simple ratio. It's a ratio. Ratio, no unit. What does the problem say? It says calculate the ratio of the resistances. So it's just a number. Okay, after you get the answer, answer this question, please. Which one has a bigger resistance, aluminum or copper, in this case? Aluminum, yeah. That's all. Okay, now you will get enough time to do number. Read the whole question. Read the whole question. Does this question say that you bought a light bulb in Europe and you're going to use the same light bulb in the US? Because if that is what the question is saying, then it's foolishness. Because that light bulb is not going to work here. Somebody tell me why. Is it going to work or will it not work?
No. I think the filament.
See, I'm trying to scramble you so you start thinking. One of this is going to not work. Buying a light bulb, you got to figure out which one. Buy a light bulb here and use it in Europe. That's one choice. Or buy a light bulb in Europe and use it here. One of this will not work. Please think and tell me which one will not.
The one that you got here.
And try to use it in
Europe.
will not work. Correct. Why?
Because it's rated for lower.
It's 240 volt. So as soon as you connect it, switch on. So if that's the case, then we got to rethink that what we said before. So what you buy in Europe will surely work here, right? Yes, it will work because the voltage is less. But is it going to be more bright or less bright? Huh?
Less bright.
Less bright. So shouldn't it be 75 divided by 4? Because power is proportional to the voltage. You see what I'm trying to say? I have to say this because last time when I said 4 times, everybody shook their heads. Now what are you going to say? One of this is correct. Think and tell me, please. 240, 120. All right, let's get it math-wise. The formula we're using is power is B squared divided by the resistance. Resistance is a constant, so I'm trying to find that out. 240 squared divided by 75. So I know that its resistance is 768 ohms. Look at the number. That's big. Remember that the length of the filament cannot be more than like 20 centimeters, right? 10 to 20. That's why Edison had to find a material called tungsten, which though small would have such a big resistance. All right, now in the US, voltage change, the resistance is the same, calculate that, you get 1/4 of that. That's what I was telling you, see? 1/4 of the power, not 4 times. I hope it's clear. So if I had asked you this problem the other way around, would you have calculated and given me 4 times, or would you have just said the light bulb will not work? I'm asking you. You know, if you had bought it in the US and then I say you use it in Europe, I almost think that you would have calculated it without thinking about the moment you use it, it will just go. Anyway, so that'll make a big difference. So think about the physics part before you bring in the math is what I'm trying to say. Okay, go to the next one. Okay, in this question it says, what is the total amount of energy stored in a 12 volt 85 ampere hour car battery when it is fully charged? Now if you look at the unit here, you find, well, of course this is the voltage, but you find an unusual unit which is ampere hour. Now that's how the power of a battery is expressed. It simply means that if this battery was being used in such a way that 85 amperes was being drawn, then it would go flat in 1 hour. So it could supply 85 amperes for 1 hour, or let's say that we were only using 1 ampere. In that case, it would work for 85 hours. So the product of the current and the time in hours should come out to be 85. Now from that definition, we know power is work over time, or power is energy over time, and therefore energy is power multiplied by time. But electrical power is the product of voltage and current. The voltage here is 12, and if we assume that 85 amperes was being drawn, then it would only last for 1 hour, which is 3600 seconds. And that's how we get 3.672 times 10 to the 6 joules. Yes, you cannot do it in kilo. Please, VI, so find the current, I1, that's supposed to be an I1. 620,000, see? That's changed into watts now, the 1,000, 3 zeros cancelled, and you get 51.67 ampere. Oh, 51.67 ampere is the current that goes to the factory. And then you find the power wasted. Power wasted is I squared times the resistance, which is square of that current times 3. So you have 8,009 joules wasted if you send it at 12,000 volt, isn't it? Now do the same. Find the current when you send it at 50,000. The current is going to be much smaller, of course, 12.4 ampere. In this case, the power wasted is square of that current times 3, which is only 461.3. What a big difference. So the change is the difference between the two. And you know that watts is joules per second. You know that, right? So we're talking about saving 7,547.7 joules every second. I hope that makes sense. You know, if you use a higher voltage, you're saving that many joules every second. Now, I think you appreciate that voltages must be really high. That's why the line voltages are really high. But before it's brought into our homes, it's stepped down to 120 volt. That make any sense? From the generating station, when it comes through the lines, the voltage is really high. The reason? To keep the current low. You got it. So when the current is low, the heat produced is really small. Otherwise, we would not get any power in our homes. By the time it reaches our homes, all of it is gone to heat the birds and the atmosphere, and it's all wasted.
Is that why you hear it if you're standing under the power lines?
That is, yeah, there are several reasons for that. The magnetic disturbance is chiefly what we hear. The sound that is produced. Yeah, because remember that energy is wasted mainly in the form of heat, but a small part of it is also wasted as sound. There you go.
So that goes for like electronic devices, other sorts too, whenever you hear like the buzzing, different sounds that some will make.
Whenever sound is produced by anything, that's energy coming out. And if you're not listening to music, that's a waste. You know what I mean? I mean, if you're using it as a heating device and you get sound, oh, you lost that much. If it's a heating device, we want all of it to be heat. If it's a lighting device, we want all of the electrical energy to be light. But in all these cases, heat is always produced. Most of the cases, sound is also produced. Isn't that what we're coming to? Conclusion? Yeah. What we can do is make them as less as possible. That's it.
So why can't we use Ohm's law to calculate current?
Okay, here it is. E, small r, caps R. That small r is the internal resistance of the battery, and I is, I've told you this is a repetition, E by R plus R, isn't it? Told you all that. The voltage across those 2 points, which is called the terminal voltage, is the current multiplied by caps R. Terminal voltage is 8.4. I'm saying that the voltages there are equal, okay, like I tried to explain, you know, I'm trying to show. 8.4 is equal to, where did I get that from? What is that? That's the current, isn't it? What is Ohm's law? That's all I wanted you to connect, but you didn't. You made it very... If you know the current that flows through this and you know its resistance, don't you know the voltage? Voltage is current multiplied by resistance. The voltage available here is 8.4, the current is 75, the resistance is R. Correct? Come on. Wait, let me stop it there. Does that make sense? What's that caps R?
Resistance of the load.
Of the load, of the starter. Now can we go ahead and find the resistance of the internal resistance? Because you have to find both. Look. You have to find what is that's 2 questions, not 1. What is the internal resistance? Is that? But we always will try to do the first thing first. That's the problem here. You know, you look at what's the internal resistance. But if you had done it backwards like I've done, it's easy. Did everybody get what I said? Because that's the second question here. What's the resistance of the starter? You won't even look at it. You will always be trying to find. But if you just use Ohm's law, get that, plug it into this equation, problem done. There it is. Now it's just math. Once you get that, you do all the algebra. It should be small. The internal resistance must be really small. Didn't I tell you it's like 0.01? You see 0.048. That's the problem done. What I meant is you would never think about using Ohm's law here. You would go through all this. 0.048 ohms. Okay, I think we should put an end to this.
I have a question.
In the seventh question here, it's a 5.80 meter length of 2 millimeter diameter wire carrying a current 750 milliampere when 22 millivolts is applied to its ends. If the drift speed is 1.7 times 10 to the negative 5 meter per second, we got to find the resistance, the resistivity, and the number of free electrons per unit volume. And to find the resistivity, we just use rho is R times A by the length and get 1.589 times 10 to the negative 8 ohm meter. You got to remember that area is pi r squared and length is 5.8 meters, and the resistance here has just been transferred. And then to find the number of electrons per unit volume, which is N, make that the subject and substitute the values of current, area of cross section, drift velocity, and the charge of the electron. And we would expect to get a high number because it's of about the order of 10 to the power 28 as we see. So that's how we do that problem. And in question 9, the battery has an EMF of 12 volt. It gives a terminal voltage of 11.8, which is less, and that's because of the internal resistance. And it's operating in a circuit with 2 light bulbs, both rated at 3 watts and 12 volt, and they are connected in parallel. And you have to find the battery's internal resistance. Now let's find the resistance of the light bulb first, and for that we use V squared by P because power is square of the voltage divided by resistance. So I've just rearranged that. Find the resistance of each bulb. It's 48 ohms and 2 of them are in parallel. Therefore, the effective resistance would be only half of that. 24 ohms is their effective resistance. And by Ohm's law, voltage is the product of current and resistance. But the current of the circuit is the EMF, which is the maximum voltage, divided by the R plus R. And that's because those two are in series with each other. And then we know that the terminal voltage is 11.8, EMF is 12, the resistance here is 24, and the internal resistance is to be calculated. Now when we do that and cross multiply and try to separate internal resistance, we will get the answer as 0.41 ohm. And the internal resistances are usually small especially for automobile batteries. It should be less than 1 ohm, much less than 1 ohm. It should be like 0.01 or as you can see 0.41 ohm. 1 ohm again would be really high for a car battery, and that would be for an electrical cell that you buy from the market, of course. Brings us to the last question, and in this last question it's a 75 watt 110 volt bulb connected in parallel with a 40 watt 110 volt bulb. So both are 110 volts, but their powers are different. We got to find the net resistance. Surely we can use the power formula that involves the voltage and the resistance and make the resistance the subject. This will give us the resistance of the filaments. Volt is 110, power is 75, so you get 161.33 ohms for the first one. Similarly, the resistance of the second light bulb would be 302.5 ohms. So if the power is smaller, the resistance is higher. And because they are in parallel to each other, the net resistance is calculated using the product divided by the sum. That only works if there are two. Okay. So in this case, there are only two resistances, so that would work. And when you calculate that, we get 105.22 ohms, and that's the answer. And I hope you could understand how all these problems were worked out. Thank you and good luck.